Thank you for your patience. Now, over to you, sir. The virtual stage is all yours.
Hey, thank you there. Hi, thank you for the introduction. Before we even start the session, I hope everybody has joined and settled in their seats. We have good number 60 odd people here. So, I mean, there's one way where I can just keep speaking of what I know and you guys can just, bear with it. The other way is maybe we can have a little interactive session and the learning could be a little more fast, I believe. So before we begin, if we can use the chat box, I believe, as the place where we can just meet each other. So if everybody can just write the place they're from and just what background are they from. So maybe just I can mold the talk in a way that it's just useful for everybody. Otherwise, I'll just be speaking on one pace and everybody will be just, not really understanding that. So which part are you from and what's your background in academics and what do you work on? And in the meanwhile, I'm just gonna keep looking at the chat box. All right, I think a couple of people have written. All right, great. So many people are from statistics, AIML, NLP. Okay, statistics, data science. Hi, Manan, good to see you. Analytics, pressure, pandas, data science, data science. Okay, perfect. So please keep writing. Yeah, data science, machine learning, great. So we have a good, well-read crowd here. So I hope you can see my screen and it's visible to you. As I said, today's session is on the power of simple models. And before even we go there, I want to start off with something very basic. I know we are all data scientists and working in this analytics field, but this one line I think is where our code. If we, I'm okay. First of all, I'm talking from a notebook perspective, not really a production perspective where you have some refactored code and things are in production. So I want to boil down things to basics first of all. So I'm sure everybody's working on good machine learning algorithms, neural networks, but let's just come down to some basics as well. Are we doing those things efficiently? And even if we are, okay, so this 1 hour, I've just divided into two sections. The first hour, the first half an hour, I'm going to talk a little more on pandas and how we can, efficiently use pandas in our pipelines or so-called analysis, the ad hoc analysis that always keeps coming. And the second half, I'm going to talk about something on the modeling side and how I've seen in many industries across different verticals, how things are easier when we do things with simple models. So I hope to convince you there as well. So let us start with pandas. So I am sure there is nobody here in these 80 odd people who has never written this line, import pandas as PD. And if you have, it's good that you are here. This talk is not for people who have never used Python, who have never imported pandas, and who have never written horrible looking pandas code. So we have a mix of good writers and bad writers. I'm going to share whatever I have learned across the years to begin with pandas. All right. So I hope you can see my notebook. I have imported some simple data. If you can also just load this data set. It's available on GitHub. And then this is a simple data set. If you know about this data set, very nice. If you are not, I'm just going to share a little bit on it. It's cars data set. So every row, it's sort of type of a car model, how many barrels it has, what kind of charge, what's the city mileage, and we have different metrics of it. Again, the purpose of this talk is not to be expert in this data set. The purpose is how we can maybe do some analyses and just pretend that we are an expert in cars and automobile industry. And this is an analysis which has been assigned to us to do. So even before we go there, I want to share some of really newbie pandas habits, which I like to call. And I think if you're doing this, you are irritating somebody who is using your outputs, or maybe you are increasing a mess in your own pandas or analysis notebooks. All right, so to begin with, writing unnecessary indexes while writing on CSV, there's nobody in here, I hope. So we have a DataFrame DF, and it's 10 rows, A and B column, random stuff. But the point is, I'm sure everybody here has written this DF to CSV somewhere or the other. And most of the times we do not use this. We simply write df.toCSV. And when I read this, I get this nonsense column which says unnamed 0. Maybe, Pandas is really writing out what index we had. And, if somebody is reading this output, they have to always write dot dropped unnamed /0 or whatever it is. And a more irritating thing is that people really read it, and then suppose they do again to CSV and you write it to the same file. Can anybody guess what will happen when I'm reading this? It's going to give me 2 unnamed columns. Okay, so the first thing that I have for you is please write index is false. It'll make the people you're working with happy and your pipelines will be much better. So when I read it, now there's no nonsense index column. Yeah, using spaces and columns names. Of course, we are all literate English people and we like to keep things nice, but specifically when you're doing something in data science, suppose I have this data frame where I have this first name, phone number, and nice name. Of course, nice name I have written is because there's no space in it. So the thing is, when you're using spaces in your columns, there's one thing that you really miss out on, and that is chaining. So if I can very well write df.nicename and I can get a series, right? Pandas has 2 data structures, data frame and data series. So I can extract a series, I can take the mean, I can do all that I want with it. I can do a rolling, whatever, 2.sum and whatever I can do with a series, but you cannot do it when you have spaces in your name. So this will just not work, right? And there are other things as well where spaces will give you problems. So a very good thing when somebody's reading your code is not to use spaces in your columns. All right, not using query method. I don't know if all of you are aware about this query method in Pandas, but if you're not, I think you're really missing out on things. Suppose I tell you that I want out of this data frame that we have autos, there's this column called barrel 8, and I want only those values which is greater than 1, and the year column is greater than 2000. And most of us are going to write this line like this. Okay, so autos, and I'm going to slice it with 2 masks. The first mask is where my barrel is greater than 1, and where the year is greater than 2000. And this will very well work. There's no problem with it. The only thing is, what if I tell you there's another way to write this? And that's as simple as using .query method from Pandas. And so you can simply write autos.query. You have this column which is greater than 1 and year is greater than 1. And you can very well just keep writing and whatever or whatever. So the thing is, when you have multiple masks to put on a data frame, it's very easy to use this .query method. And if you are coming from a background of data engineering and SQL and Postgres and that sort of stuff, then I think this is just a boon for you to use Pandas with, because it just takes in all the sort of SQL syntaxes and integrate within Pandas. So if you're not using this, you're really missing out on something. And it's easy for somebody to read this. So suppose if you were to read a code like this, it just might be a little hard for the eye, and somebody especially not familiar with Python or Pandas syntax, and versus a query method read is a lot easier. All right, moving forward, if you have been an old user of Python and you have never upgraded to Python 3.9, I believe f-strings were introduced in, and if you're not using f-strings, you're missing out on something again. So earlier in Python 2 and earlier versions of Python 3, if we had to concatenate variables, which are string variables, inside a string, we would write some things like this. And people used to write actually things like, name to write CSV files like this. But the thing is, this of course will work. Nobody is stopping you from doing this. So you put on variables by doing this like plus, and in Excel, you do basically ands. So this is somewhat like Excel structure, but if you're doing Python smartly, then there's this new thing called f-strings, and you just simply use this. And the thing is that you can just put an f before you start a string, and then you keep writing in curly brackets whatever variables you want to insert. And this is going to print out the same things. And if you're super smart and you're using Pandas with f-strings, you can say that I can use my query strings to be an f-string. So there are many times when you're creating functions and you're processing data frames. These are simple things, but if you can just use them wisely wherever you want to use them, then I think they could really be a source of real good code writing skills in Pandas. So again, you might have some parameters in your functions and you're trying to process that data frame. Then you can simply use query method and you can just pass on your filter columns, filter values, and things like that from your parameters of a function. And this will give you the same exact answer. All right, using vectorized functions instead of for loops. Python is a slow language and for loops make it even more slower. So the whole idea of using for loops is kind of the last resort that you should have. So suppose you have this data frame and I tell you, okay, I want another column which says if the car is new or not. And the criteria for it is if the year column is greater than 2000. And there could be, this is a simple example, but this could go on a little more complicated. And the way you suppose you don't know any vectorized function. So you say, okay, maybe I'm going to do a for loop, which is the first instinct for the people who are at least beginning it. I know there could be a lot of experts here in the audience, but this is more for the people who had just begun and maybe they could just speed things up. This is going to work, this block of code that I've just highlighted, and it's going to create a true-false column if the year is greater than 2000 for every row. I hope you're familiar with .iterRows method of Pandas. It returns the index and the row as a series. And this will work, there's no problem. But if you knew vectorized functions, you can just simply say if my autos year column, which is going to be a series, is greater than 2000, it's again going to return you a series of Boolean. And if you just try to time it, you will see the difference that I'm speaking of. Okay, some people say I can use .apply and I think I'm pretty smart. Well, in the background, if you do not know, .apply is actually equivalent to using a for loop. So for loops and .apply methods should be your last resort when you're actually writing Pandas code. Not to say that it's bad, but if you have a better way of doing it, always resort to that. All right, just taking things quickly so we can finish Pandas. Yeah, treating a slice of data frame as if it was a new copy. So I'm going to run the cell and just give me a heads up on the chat box who have all come across this warning, which says trying to use .lock instead of a value is trying to be set on a copy of slice of it from a data frame. And at least in the beginning days, you can just never figure out what's really happening. So the thing is, suppose you just slice a data frame and I'm using .query method here that the year is greater than 2000. So all the rows from autos to where the year was greater than 2000, make it into a not new variable, I'll call it, but let's just assign another name to that. And then we apply some statistic, some function to this slice of data frame. And that's why it gives you a warning because you're actually replacing those rows in the original data frame. So Pandas is trying to tell you, hey, if you're trying to do something like this, please use .copy method. So the whole suggestion here is if you, of course, we slice data frames often. So just use .copy method even before you try to do anything, and you will never run into these ugly warnings. Okay, using string values rather than Boolean, Pandas is memory heavy. It uses heavy memory. So even if you have a 200 MB CSV file, if you read it in Pandas, it's going to be greater than 200. And integers, float values, datetime objects, and categories are all fine. They're memory optimized, but it's really bad in Pandas if you are using string columns. Of course, we cannot avoid them, but wherever you can, try to use Boolean or category data types of Pandas itself. A string like no or yes kind of destroys the purpose of rather than you won't have that column for. So try to use Boolean wherever you can. This is something very basic, not repeating code. I've seen many people write such things. That's why I have this. So suppose you're trying to do the exact same operation on two slices of a data frame, and then you have the same process repeating over two data frames again. Please use a function and just pass through that. Okay, the last newbie habit is sometimes we have this. Suppose you're trying to just rename a column and you just print out all the columns, paste it like this, and you just want to change one of the columns. So you change this value here, city, whatever, city underscore mileage, and you run this. It'll run, but this is, I think, the worst way of renaming. You could do many blunders while doing this when Pandas gives you such a nice method of autos.rename where you can just pass on the column for the new name versus the old name that you have. So this was some of the few very basic Pandas stuff that I'm sure everybody is already familiar with, but things like this can really make an impact. Okay, so I told you about the worst of pandas. I want to introduce the best of pandas as well. So the next 15 minutes, I'm going to share something, some of the things that I've learned best about pandas. I'm going to be a little quick, and if you think it's really a fast pace, you can please let me know in the chat box, and I'll be more than happy to slow down. All right, so if there is such a thing, what I can do is, all right. I hope somebody doesn't say I didn't write index equal to false, but that's all fine. All right, and we have that. Maybe I'm going to just. All right, so we have this that autos data frame again, and I'm just welcoming you to Better Pandas. And the first thing I want to talk about is data types. Many times when we're doing analysis, it's not a mere small 20 MB, 30 MB CSV files or data frames which are such small in scale. Sometimes we have millions of rows and we're trying to do something via pandas. It might not just be an analysis, but even before you're coming down to your machine learning part or fitting your regressors, estimators, whatever, you have a lot of things, a lot of code through which the data frame really passes through. You have many pandas processes like that. And I just want to suggest a few things that can make it really well. So looking at the data frame itself, it's fine. So I have these columns with me. So let us only look at the subset of columns. I'm just looking at the data types of it. Okay, these are some of data types that pandas infer itself. So we don't have a lot of control there. You can pass it actually while reading a CSV if you know the data beforehand. But suppose you do not. And there's this pandas method called memory usage. And if you write deep equal to true, you will get every column and the number of bytes that the column is actually using on your memory. And if you just try to sum it, so this mere simple data set is consuming 19 megabytes, 19.64 to be specific, on my RAM. So if I want to just select maybe integer columns and see if they really need to be integers, and if I'm not wrong, they're integer 64 objects. This is really small stuff, but I just want to highlight this. Do I really need 64 bits to really store this variable and the values inside it? Maybe, maybe not. So let's just check that. And I think for some things, integer 8 and integer 16 will just float. So if I try to do that and just do the same thing, describe, and then I check it, okay, from 19, I've reduced it to 18. Let's just try for float columns as well. So if I just, there are only 2 float columns I have. Okay, now cylinders. I'm sure in every car, the cylinder is an integer. You can't have 8.2 cylinders or 4.2 cylinders. You only have 4-stroke engine or whatever, 4 cylinders engine, right? Can anybody tell me why Pandas has still managed to give it a float value if all the values were inside it are integers? And maybe I can just prove my point by saying talent is unique. And if I check the values, they're mostly integer values. Why did pandas really do that as a float? Okay, I'll answer that. So it's actually because of this nan. Nans are not supported in pandas. So if there is any nan in a column, it can never be an integer column. It can only be a float value. That's why pandas did that. But if we can simply just check where there are NAs, so we check the cylinders where their NAs are actually EVs. So maybe EVs don't use cylinders. I don't know. I'm not an automobile expert, but it seems like that. And if we can just change the data types for these columns and just fill the NA values and then change my cylinders column to integer and displacements to just float 16 rather than 64 objects, maybe I just save 1 meg more. The real magic comes when you try to do the same things for object columns. So suppose I select these columns where this data type is object. And if I just want to see things there, and I'm just seeing where drive is NA first, and I just skip forward maybe to more important stuff, I'm just creating the other 2 category. And if I just change this one type from object to category, I just saved quite a lot of memory. It was 19.6 to begin with, and now I'm at 12. All right, I'm just looking at another column, which is tranny. I'm not sure what it stands for, but the values are automatic 4-speed, manual 5-speed, and things like that. So I'm just trying to extract the same things from tranny and then changing the data type for it. And now I see that from 19, I can even boil it down to 10. If I just do everything right with my date column as well. And then you can see I can boil from 19 to 7. So the point is that this data set is small. When you have a data set which is, I don't know, 1 GB, which is taking that space, even if you're trying to do mean or simple statistics, Pandas generally tends to take time because the data types it's seeing, it has to do a lot of computation in the background. You can't really blame Pandas for it. But if you do just a simple thing of assigning correct D types, even before you start any analysis or your model building pipelines, they'll be much faster and efficient. All right. So I just created this function of whatever we have done, just changing the as types, filling some NAs and things like that. And I've just created this autos2 data frame in line 36. So I want to introduce the second thing, which is important in Pandas, called chaining. If you're not if you have never heard this term, Pandas chaining or flow programming, then maybe this could be really good introduction for you. And the real point is that rather than making intermediate variables, we'll just leverage the fact that most operations return a new object and work on that. So you're always trying to perform an operation on a data frame or a slice of a data frame and then return that data frame and then do something again with that data frame. And it just creates a lot of mess in our code. So I'll just explain what do I mean. So suppose I have these columns and I tell you, can you just select subset of columns from the master data frame, fill NA for a particular column, assign the integer 8 data type to this column, and then replace the same thing on the data frame. So I'm sure some people might just write it like this. Okay, I can select it, just, slice the data frame with the columns that I have. I can do fill NA, create another variable. I can assign the type, maybe create another variable, and then on the data frame itself, I can overwrite it like this. It's messy. It doesn't look good, but what if I tell you there's a better way? And that's what exhibit A that I've just selected. So I say in the line 1, this is called Pandas chaining. You keep doing dot operations, and if you wrap them around in a parenthesis, it's really easy for people to read your code. If you're giving your code to me, I'm reviewing your code. It's just so much easy for my eyes to read this code versus the code above, right? So it simply says from this autos data frame, I'm selecting some columns. So far, so good. Okay, I'm replacing the cylinders column, or I'm making the cylinders column. And then I'm doing from this data frame, this cylinders column, fill NA, perfect. And then I'm just assigning the data types of the same column, perfect. And this will return the exact same thing without any errors, without making any messy variables in between. And it just looks better. I'm sure people will agree with me, but the thing is, we don't do these simple analysis. Generally, our code looks like this, what's in front of you. So we don't just do that simple code, right? We just don't write four lines of Pandas code and say, okay, we have processed our data frame or whatever analysis we have done. But this is what sometimes our code looks like. How many of you really agree with this? Right? Even if you created functions, many times subset of inside the function, the code could look like this, right? The whole point is making global variables to use extra memory, mess to read. Your friends won't be happy and you won't be happy to come back and check. If I tell you can you just change that? It'll just take you a little more time to just change a few things. And on top of everything, it's buggy. All right. Compare this mess to this chain. It's so simple to read, easy on the eyes. I know exactly what's going on. And the best part is you can just simply start to comment out stuff wherever you want to, whatever part of the process you want to eliminate. It'll return you exactly the same thing. But the thing is, it's just so easy to read, isn't it? All right. So this is exhibit chaining, the first thing. I know the chaining part and changing the data types for such a small data frame might not look well to your eyes, but I have another data frame which I have here, and it's just reading. I had the CSV file. And once the CSV file is done, in line number 2, I'm just printing out the number of rows it has. And then I am simply chaining a few stuff. I'm copying it, and then I'm assigning the date column to be a date type and renaming a few columns, selecting a few columns in line 10, assigning types, and then just simply resetting the index. And if I just run that, in my raw memory, the data set was using almost 2,400 of megabytes. And once I've created and assigned proper D types, it has just boiled down. Yeah, so there you go. It has 8.5 million rows. And then once I've just created the simple data checks and easy to read chaining methodology of writing Pandas code, I can simply boil it down to 233 megabytes. All right. So these are a couple of things that I thought would be best to highlight. I don't think I'll be covering master aggregations. This is pretty easy stuff, but I hope till here, whatever Pandas you saw, you would be able to do things better with. In master aggregations, I have things where you could just simply do group bys, and again, just keep using chaining, and then keep aligning your query methods or whatever dot methods you can have from Pandas after your group bys, and then which makes your pipelines and your analyses a lot better. All right, simple things like if you have large number of columns, if you have like hundreds of columns, and you do a dot group by, and suppose you do dot mean, and after that you select your columns like this, it's just going to take a little more time because it has to compute mean for all of them and then give you these columns. A better way of doing this is first to write after group by the columns that you want and then do dot mean. It's going to give you the same result, but a little more efficient way. Because I know in production, every second of your runtime really matters. Many people are not used to using dot plot of Pandas, which is really handy to check quick trends and things that you just want to infer from the data set, but not really present. And that's why dot plot method could be chained along with your Pandas stuff that you have. All right, so let us move to the second part of the talk that I have, and which is on power of simple models. All this is covered. So I just introduced the topic. I'll talk are we focused on the problem or the solution? I'll talk about the summary of this topic, the XOR problem, the practical. I'll just show you what I really mean by all this. I'll conclude with my takeaways from it, and then we can open for QAs for this session. All right, I think this summary has already covered. All right, many times when we are reading stuff on YouTube and wherever we are, most of the times looking at stuff, you come across it that you should be using deep learning and more sophisticated models. If you have somebody senior at the office, maybe they are very well off with complex algorithms and much complex pipelines, they simply say, hey, you're using linear stuff. Is that really required? You should be using deep learning. You should be using sophisticated models, and all over blogs, Reddit, Hacker News, YouTube stars will keep telling you that. I have a little different opinion. Are we really focused on the problem or the solution? And in fact, it bugs me these days because it's getting a little overwhelming and feels like people are, and all of the peers, whoever I see, are focusing more about the tools that you want to learn rather than just focusing on the problem that you're trying to solve. And I've applied deep learning in production. I've applied many complex models across my tenure of the last 8 years or so, but I really prefer simple models. And I'll just try to lure you into the same domain of our old boring linear models with this half an hour that I have left. All right. And yeah, there's this famous saying that when you understand the solution of the problem better than the problem itself, then something is really wrong. So you are always focused on the solution that you have built, but you're never really thinking of what the problem is at hand. And when you're trying to understand your solution itself and trying to prove a point to the people who you're supposed to convince that machine learning is great, then something is definitely wrong. You're not really thinking in the right direction. So just an example, suppose you're trying to make a recommender system and you're not recommending the next episode that somebody is seeing, and you've built a great, nice deep learning model. If you're not suggesting the next episode, I'm sorry, something is wrong. Okay, so, and it's not like deep learning and complex model aren't amazing. There's a lot of good stuff happening there. I know a lot of people across multiple companies who are doing just amazing work in deep learning, but the hype around them is really, really dangerous these days. Everybody's trying to learn RNNs, LSTMs. Nobody wants to learn ARIMA to begin with. And you may be doing yourself short if you just pay attention to all this jazz and all this hype that is being built around deep learning or complex models. And you can really often win with simpler models. Suppose you have a 4-member team of data scientists and everybody's trying to, dig into a problem, and everybody has made a good architecture of deep learning models. You can. What would you say if I tell you might even with a simple model, which could have properties which are much nicer in situations beyond a Jupyter notebook? So as I said, my goal is to make you believe that the domain of more old but ultimately beautiful simple model is really worth exploring before you move ahead to complex algorithms or models. And in order to exhibit that in front of you, I have the XOR problem. So what I want you to do is, it's a small practical. I want all of you to just Google this word XOR problem. And I'll just take a pause for a minute. And I just want you to Google this term XOR problem. And just keep that tab aside and come back to the presentation. Okay, so this XOR problem is a problem where the data set is such that you cannot use a single line to split it. So on the right-hand side, if I have this distribution across two X1 and X2 feature space, and I have this blue and red dots, and I tell you, hey, can you build a model to just so I can have a decision boundary which separates these two type of colors. And the problem that you, the verbatim that you come ahead with in front of me is that there's no linear model that I can fit which can do this. Agreed? And that's the main argument you really hear against linear models. And the first point where any academic person or even an industry person will come, hey, you cannot solve the XOR problem. Well, and every textbook on neural networks has this example to begin with. And if I tell you that now, if your Google search would somewhat say the same thing, right? So I'll just show you the notebook that I prepared and just maybe try to say what I want to say from this. All right, I hope you can see my screen. And I just want to explain everything that I'm doing, so there's no hidden things up my sleeve while I'm doing this. So just standard imports I have. The only thing which you might not be using a lot is Patsy. So this is a library which actually I moved to Python from R. In R, we used to just give in formulas where we used to say a target variable, tilde, and then all the independent variables plus. So this sort of gives us an API that we can write sort of R stuff more into Python. And that's how I moved to Python a few years back. So the XOR problem, if you have Googled it, if you're following me, this is the verbose that Google might have come up with, that the XOR problem is that we need to build a neural network, a perceptron in our case, to produce a truth table related to the XOR logical operator. So this is a binary classification problem, and supervised learning is a better way to solve it. In this case, we'll be using perceptron. So I don't know how many of you really arrived at the same result, but I think it should be common for most of us. So again, the idea is I have a couple of distributions in front of you, sort of these handmade images, and I want to create a model which can separate these two. And of course, since the talk is about simple models, I want to be as simple as I can in my modeling stuff. All right, so to prove my point and to really explore this hypothesis that the XOR problem cannot be solved with a linear model, and you need a neural network to really solve this problem, or not neural network, but you need a really complex non-linear model to solve this. So let us create a data set and explore that hypothesis. So to explain the code, in line 1, I'm just setting a seed. In line 2, I'm creating a random X array with RNG random number and 750 samples I'm creating. And then Y array, I'm using the logical XOR operator from NumPy, and I'm just passing my X array to that. So I have a data frame. I'm sorry, I'm trying the notebook. All right, and I have a data frame with X array as columns is X1 and X2, and I'm creating 2 columns for my X's. And then my Y series is a Pandas series where I have the Y array from the above cell, and I'm just naming it as type. So my model DF actually looks like X1 and X2 and a type, which is exactly this thing that I want to create. And if I just visualize the same thing, and this is some redundant code, it's pretty easy. But the thing is, on your x-axis, you have your x1, on y-axis, you have your x2, and you have the distribution as a scatter plot colored by the type, which is our target variable here. All right. And again, we want to create a model which can separate out these 2 colors, and it is still simple. Okay. So people say we need a neural network to solve the problem or some complicated nonlinear model. Let's revisit that now. So I hope everybody is following the problem that we have at hand. It's again called the XOR problem. On a 2-dimension feature space, we have this distribution, and we want to separate out these colors, right? Okay, so let us first of all visit and call our dear not so cool friend, which is a linear model on logistic regression. And let us just implement that straight away and see what the confusion matrix looks like, even on the train set. Since we are not doing train test split, we just want to see if we can make a decision boundary, a model which can, sort of distinguish between these 2 colors. We are not doing any train test splits. We just want to see on the train set itself if any model can do that for us. All right. And I have created decision boundaries as well, which can help you in sort of deciphering stuff that I am displaying. All right, so again, just explain the code. This is redundant imports, pretty simple, just importing logistic regression, confusion matrix display, and a classification report for my metrics from the CM. So I have Y and X, and this is where I'm using patCSD matrices, and I'm saying that my type variable is the target variable, and which is nothing but a function of X1 and X2, and all these reside in this data frame. And in line 2, I simply fit a logistic regression with my X and Y, and I do dot predict on my X itself. And I get a confusion matrix, and I create a classification report, which is in front of you, and you will say it's pathetic model. The F1 scores for your negative class is 0.68, or one of the classes is 0.68, and the second classes for your 1 is 0.01. So that's sort of, there's no way this model can even make up to your manager, or you can even show your face if you have created such a model. And that is why, let us just look at the decision boundary just for the sake of it. And this is our initial logistic model. I'm just doing this thing again with my X and Y. I fit the model, and then I'm just creating the decision boundary. I'm not getting into this code because it's simply just reshaping things, creating a mesh grid to create the decision boundary. So if I see, this is what my plot looks like, and my model, which is trying to, give you the colors of probability, there's no way I can separate this. And that is what is reflected from the confusion matrix as well. So this is the part what I'm talking about, 0.68 and 0.01. And if you really look at, the logistic regression lets you classify new samples, right? Based on any threshold you want. It can give you probabilities as well. But generally, people use a 0.5, and that is why I've created the decision space. And if I just cut it on 0.5, this is the decision boundary that you're going to get. So there's no way this model is fine. And I think if you had this at work, this problem, and if logistic regression gave you this result, most of you would have done what I'm trying to do now. So it's pretty awful. Our instinct in such cases is to move towards more complex algorithms, and ones which are easier to implement than to understand. And it's important. It's a little sarcastic. I wrote that because many people do not really understand what SVM is doing under the hood. What do the parameters do? How does it really create the hyperplanes that we speak of? But it's easier to implement than to really understand it. So exhibit A, a support vector machine, let's say. We import support vector machine, and just like anybody else, I'm just doing my X and Y as my patCSD matrices. I do a dot fit with my SVC in line 2. I create the same confusion matrix, I display it, and then I just create the classification report as well. And you can see I create an F1 score for 96 and 95 for both of my classes, and that's there. You go ahead for this production, but even before you do that, and the confusion matrix, this looks great, right? and you're really happy, you just check the decision space as well for SVMs, just doing the same with probably equal to true because I'm trying to create a probability decision space. And if I just do everything right, I can see here that my just decision space looks beautiful, and I can simply distinguish between the red and the blue areas. From this model, there's no way I can, anytime let go. I mean, my accuracy is always going to be high, and all my metrics, F1 scores, specificity, precisions, everything is going to be well. Let's just be happy with this model. And if I just try to, from the probability space, come back to cutting at 0.5, give you the decision boundary, this is what the decision boundary will look like for this SVM. And of course, you're really happy with this model. And you go with, oh, wow, and you just put this into production. And then after a few days, one day you wake up to a call on a holiday that the model has broken and you have no clue what has gone wrong inside the SVM. And there are aspects of such algorithms which are really hard to comprehend, right? And you do not want to wake up on a Sunday morning, or I do not want to wake up on a Sunday morning, getting a call from office saying your model has broken, the predictions are all over the place. Can you just fix it? I don't want to spend my Sunday fixing an SVM, right? So let's take a pause here and think, can we do something else to still be awesome and remain in the linear domain? Suppose I'm not really confident about SVMs. If the client asks me to derive the SVM hyperplane, I cannot do that, let's say, right? So I still want to make a great model. I do not want to be focused on what algorithm am I using, but on the problem at hand. So let's go back to our high schools. If this was a problem for 11th, 12th grade, what would you say, right? Maybe we somehow apply a neat little trick which can separate the points and still be using our linear model. Suppose logistic regression was the only algorithm that you knew. What would you do then? And you say, okay, let's go back to feature engineering, okay? And then let's just do something very simple. Maybe you try to transform it, but you just come up with an idea, which I have for you, is maybe we just multiply these two variables itself, okay? So again, this is the problem that we have at hand, the 2 points that we're trying to separate. And then I simply add one line of code, which is model DF. I create a new variable x3, which is a multiplication of these two columns. And now my formula matrices look like y and x with patsy.d matrices. I'm saying my type is now a function of all these three variables inside this model DF. And then I fit a logistic regression again. I generate my confusion matrices. I generate the classification report, and voila. I mean, your F1 scores and your matrix just looks awesome. And honestly, tell me how many of you would really give a logistic regression a second chance rather than going with an SVM. And if I just look at the decision space for my decision boundary and the decision space for logistic regression, this is the new feature I have. So X1 and X2 was distributed like this. There was no way I can fit a linear line. But the moment I created a new feature, which was X3, and on the plot on the right, you see X1 and X3 on your X and Y. And then you created a logistic regression. It was very well able to separate the points based on this new plane, or the new plane that new dimension that you added to the Cartesian 2D plane that you had earlier. Okay, so my point is, again, just to highlight and to be a little more showcasing it, you have good results with a logistic regression. Maybe it can compete with your SVM itself. So again, my point is XOR can be solved with a linear model with just adding one line of code. People don't want to spend that time into feature engineering. People, and most of us, frankly, when we come into this industry, we want to apply complex models that can solve simple problems, right? And now we have a logistic regression, which is easy to explain and less stuff goes wrong in production. Because essentially, once I've created a model, I'm not going to run it in a notebook forever. It's going to go in production. I'm going to refactor it and I'm going to put it in production. And logistic regression, it's so much easy to handle in production. If something is wrong, you can very well just pinpoint the location, what's going wrong while it's going in, your data is going inside logistic regression. So I just want to inspire you towards feature engineering can save the day. It makes just sense to come up with systems than just mere fit predict algorithms. I hope everybody's catching what I'm trying to say. Like in SVM, we just dot fitting, dot predicting, and it just makes a little more sense. And I think our smartness would really be appreciated when we try to do stuff which is simple and yet effective. And of course, simple algorithms can have properties that complex models are missing out. There's no way you can get your coefficients, or if a predictor, an independent variable, a feature is really important, how much is it impacting on your dependent variable, for which you apply another sharp model, and then you confuse the client of what really metrics you are talking about. But in the case of logistic regression, linear regression, you can tell them coefficients, you can tell them exactly by what degree is your independent variable affecting your target, right? And we should care more about than just error in the test, right? And if you're just starting out, if you are always focused on the test error, I think that's not really good modeling. Rather than we should be providing a service than just telling the client, hey, this is the test error that I'm getting, or anybody else for that matter. Also, just want to highlight a lot of stuff has been taken from this Winster Warmadam. He is a great data scientist out there in the UK. All right, so getting back to our presentation, we have practical. I hope I have convinced you that linear models are not that bad. And we just gave a demo that linear method can really solve a nonlinear problem, which it seemed like in the first place. And I said, because the model is linear, we gain properties like we can apply regularization tricks. We can do a custom loss function, things like that. You can have better interpretability, right? And as a consultant, it's easier for me to leave a linear model at a client location. And even if they're just starting out with the data journey, even if they're not running Python, if they're not running R, even if they're running JavaScript or Java or anything, I'm sure anywhere I can apply a linear regression. I can do a logistic regression. Every sort of legacy software or legacy or any old language has the support where I can build that. So linear models are not that bad. And I hope this example spoke to your intuition and gave an insight that feature engineering tricks can really actually be a lifesaver. You can still be in the realm of boring, old, nice linear models and still make a pretty good system. I wouldn't call a nice model, but a really good system, a forecasting system or a prediction system. And I hope this made you think about the holistic solution than just which model to apply. Many people just like a bag full of, I don't know, called guns, different guns. They see a data set and they just try to fire all the guns on the data frame. Maybe just take some time, look at the data frame, look at the distributions, what are like, create some features, try out linear regression, try out the basic stuff that you know, and see how it just performs against all the complex things. And this is Occam's razor, even if you go into deep learning stuff, which says that the best model, even in deep learning, are the ones which can have less complexity and better accuracies, right? So even if you try to just apply across the ML umbrella, then you might be saying, maybe I should start off with the basic stuff first. So next time you hear from someone that, oh, you've just created a linear regression to solve this, and if you're convinced that this model is great and it works, then just take a moment and pat yourself on the back that you've been able to think about the solution, then just which model to apply. I think it's the time we can have Q&A. So we can also finish on time. I'm just looking at the question answer session. If you have written it, or if you're still to write it, please go
sorry
ahead.
to interrupt, sir. Well, guys, before we proceed to your questions, I would like to request attendees to please fill the feedback poll, as it helps us to conduct more such sessions. And you can proceed with the Q&A, sir.
So I hope I'm just giving it a minute so all of you just focus on this thing that has come on the screen so I can answer the questions. All right, so I'm just starting with the questions. Somebody has asked, is it good to have different integer sizes or make standard integer 64? I would say if your data set is small, if you can have the time to really do that stuff, maybe just try to do integer 64, 16, 32, whatever you can. But if you don't have that time, then integers do not really take that much of space in your RAM anytime. So you're good with integers. Is there a chaining documentation source? Yes, there is. There's actually this person called Matt Harrison, who is one of the founding members in Pandas journey. I think it started off in 2008, Pandas. And he has written a book, and he has a few talks as well on the web, on YouTube, and on PyData as well. If you're not following PyData, I really highly recommend that you do that. There he has explained chaining, and you can have other sources as well. Just try to Google Pandas chaining, and you will come across a lot of good stuff. Ayush says, can we use kernel SVM here to distinguish between two classes in XOR problem? Yes, absolutely. That's what was happening. That's exactly why SVM gave you a good result, because you were using a nonlinear kernel. But what I'm saying is, why do you even need to go to that complexity of using a nonlinear kernel? Maybe just start off with something like creating an extra feature, right? I'm not saying SVMs are bad. I'm not saying nonlinear kernels are bad. What I'm saying is start from simple stuff. Anand says SVMs are also linear classification algorithms, correct? Unless kernelized. Yes, exactly. How did it generate nonlinear decision boundaries? Because I think the default in SVMs uses a nonlinear kernel. And I did not specify any kernel while fitting SVM. Ayush says, or we can use kernel with logistic regression. Yeah, absolutely you can. See, till the time you remain simple, till the time you're able to make out good systems, just do whatever you feel like. The whole point of this talk was to just try out simple stuff first before thoroughly, and convince yourself there's nothing more that I could do to be awesome and still be linear, or still use simple things, not even linear, simple things, before you move out to more complex things like SVMs. So could you upload this stuff on GitHub and share that, please? That was a wonderful session. Thank you. Shubham says, can you please suggest the way to improve the DF handling skills and feature engineering skills? Yeah. All right. DF handling skills, try to be better in Pandas. The more, I would just call it more better, beautiful code you write, you will be inspired yourself to try out new things, and you'll be able to handle your data frames so much easily, I tell you. Feature engineering skills, first of all, you need to really understand the data set. Never approach a data set blindly without knowing what the data set is about. If I was given this scarce data set, I would really take my time to research everything that I can about each variable. So I work in weather sciences, across marketing, sales, all sort of domains across data, except for medical. I do make sure that I give my time to research about the data set of what each variable really means in a sense. Mayank says, you have made me realize I know Kiddish Python. We've all been there, Mayank. Don't worry. Oh, yeah. So Manan says, could we square the values in XOR problem? And that's exactly what I want your mind to come at. Why not try these transformations before moving to SVMs, before moving to your random forest, before moving to deep learning? Try out these different transformations, trying to extract features of the information you have before moving there. I'm not saying don't move there, but if we could have squared those, transformed those, maybe just try that for yourself, Manan, and let me know. Yogesh says, features in the model, you use X1, X2, and X3. Yes, absolutely, Yogesh. Those are the features I used in the second iteration of logistic regression after I created X3. In the first iteration, there was no X3. Can we just use X1 and X3? Yes, absolutely. Once you have X3, you will see how X1 and X2 are sort of redundant. Okay, yeah, please conduct more such sessions. That's for analytics Vidya, I believe. Anand says, are there any provisions for parallel processing of data frame in Pandas? Or do we have to rely on other packages? Okay, so he has picked, I think, the final resort of Pandas. Pandas does not support parallel processing at the moment. I hope they do. It's a wonderful library. But there are newer packages, which are, one of them is called Polars, if you've heard of Polars. It does support parallel processing, and there are a host of other things, Dask. There's a whole family these days of Python packages which support bigger data frames. I'm not going to call it big data, but yeah, large data frames you can process easily there. But if you're really smart, you can really handle a good amount of data in Pandas itself, I would say. All right, this was all that there was from my side. If you have any more questions, I would love to address them.
Okay, thanks a lot, Vasudev sir. On behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. And guys, I hope everyone has filled in the feedback poll. If not, I request you to please do so, as the feedback is valuable and helps us to conduct more such knowledgeable sessions. And we will be back with another session of DataHour tomorrow. The links of upcoming sessions are in the chat section. Till then, bye-bye and keep learning.